A solution is formed when aggregated solute is combined with aggregated solvent. An example is combining solid sodium chloride with water to make a saltwater solution. Together, the solute and solvent before they are mixed is the initial state, and the solution is the final state. The enthalpy change that takes place during this process is called the enthalpy of solution or the heat of solution, and is given the symbol delta H sub SOLN, which most people just call the heat of solution. In this description, solution formation takes place in a single step from the initial state to the final state. Thus, the enthalpy change for solution formation is the enthalpy of the final state minus the enthalpy of the initial state. But because enthalpy changes are independent of path, we are free to devise a multi-step process for solution formation so long as the initial and the final state are the same. The multi-step process that was devised in another microlecture involved 3 steps. In the first of those 3 steps, aggregated solute particles are separated. This is always an endothermic process, and the enthalpy change for this step is given the symbol delta H sub solute. In the second step, aggregated solvent particles are separated from each other. This is always an endothermic process, and the enthalpy change for this step is given the symbol delta H solvent. In the third step, separated solute particles are combined with separated solvent particles to form the solution. The enthalpy change for this step is always exothermic, and the symbol for the enthalpy change is delta H mix. To better understand these steps and how they are helpful, we can examine the enthalpy changes on an enthalpy diagram. In an enthalpy diagram, enthalpy increases along the vertical axis and horizontal lines are drawn to represent the enthalpy of states of the system. Solution formation begins with aggregated solute and aggregated solvent, which together have some enthalpy. Step 1 is to separate the solute particles so that we have separated solute particles and aggregated solvent. This has some enthalpy that is higher than where we started, and the enthalpy change during this process is called delta H solute. Step 2 is to separate the solvent particles from each other so that we have separated solute and separated solvent particles. These have some enthalpy larger than either one of the previous 2 states, and the enthalpy change for this process is delta H solvent. Step 3 is to allow separated solute and solvent particles to mix to form the solution. This process has an enthalpy change called delta H mix, and it is always negative, which is indicated by the downward pointing arrow. Delta H mix is always negative because of the favorable attractive interactions between solute and solvent particles. This leads to a solution enthalpy that is lower than the enthalpy of the separated solute and solvent particles. The way we have drawn the diagram, the enthalpy of the solution is higher than the enthalpy of the aggregated solute and aggregated solvent. The net change in enthalpy between the initial and the final state is therefore positive, and we know this is called the heat of solution. This is therefore the enthalpy diagram for an endothermic solution formation. Note the 3 steps form a cycle that first takes the system up to some higher enthalpy, that's the cost associated with breaking solute-solute and solvent-solvent interactions, and then lowers the system back down to the enthalpy of the solution. That's the return when forming new solute-solvent interactions. The net result is to go from initial state to final state with the heat of solution. Here, the costs are higher than the return, so the process is endothermic. Of course, the enthalpy change does not have to be positive. Let's look at an enthalpy diagram for exothermic solution formation. Again, enthalpy increases from bottom to top. Solution formation begins with aggregated solute and aggregated solvent, which together have some enthalpy. Step 1 is to separate the solute particles so that we have separated solute particles and aggregated solvent particles with a higher enthalpy. The enthalpy change during this process is delta H solute. Step 2 is to separate the solvent particles from each other so that we have separated solute particles and separated solvent particles at an even higher enthalpy. The enthalpy change for this process is delta H solvent. Step 3 is to allow separated solute and solvent particles to mix to form the solution. The enthalpy change is delta H mix. The enthalpy of the solution is lower than the enthalpy of the aggregated solute and aggregated solvent. The net change in enthalpy between the initial and the final state, the heat of solution, is therefore negative, giving an exothermic solution formation. In this case, the return from forming new solute-solvent interactions is higher than the cost of breaking the solute-solute and solvent-solvent interactions, giving the net exothermic solution process. Let's compare the endothermic and exothermic enthalpy diagrams to see what they tell us. If we carefully compare the enthalpy diagrams for the endothermic and exothermic solution formation, you'll notice that the difference between the two is the length of the arrow for delta H mix, the enthalpy change for solute-solvent interaction. We can now answer the question, why is the heat of solution negative in one case and positive in the other? For this example, the answer is that solution formation has the same cost in each case, delta H solute plus delta H solvent, but the return, delta H mix, is more negative in the exothermic case, meaning that the solute solute-solvent interactions are stronger in the exothermic case. In reality, comparisons like this are more complicated because it is unlikely that delta H mix could be changed without also changing the solute-solute interactions and the length of the delta H solute arrow, but the main point is that we now have a way to discuss solution formation in terms of 3 physically meaningful steps, which is not what we had at the start. And that's enthalpy diagrams for solution formation.